Welcome everyone to section number 5. This is curl and divergence. So in this video, right, we're going to give you some definitions. We're going to be able to show actually finally that when you have vector fields, right, that go from R3 to R3, what does it take for these things to be conservative? We'll tackle that here in this video. And then finally, we'll actually calculate out some potential functions. All right, so let's get to it. A definition of curl and divergence. And actually, before we get to that, I have to give you a new operator, right? It's called a differential operator. It's pronounced as del, right? And it just looks like this upside down triangle that we used in the gradient. And what this means is just it's a vector, and in the first component it's the partial with respect to x, in the second component it's the partial with respect to y, and in the third component it's the partial with respect to z. Now on its own, this is kind of a sad object, right? It doesn't really mean a lot, right, unless if you say what to take a partial with respect to, right? And so you don't usually see this thing, sitting by itself, but it acts on vector fields. And so we can act on it in vector fields in a couple different ways. And in the first way, you get the curl. Oops, there we go. Curl of f. Again, you define this maybe in R3 or something like this. And so the curl of your vector field f is what happens when you take this del operator and you do the cross product along with your vector field f. Okay, so if we wanted to calculate out this cross product, right, so this would be the determinant of a matrix. And cross product, you have I, j, and k in the top row. And now next comes your del operator. So del, so the partial with respect to x, the partial with respect to y, the partial with respect to z. And then f. Well, f usually has components like p's and q's and r's, things like this. And so when you take the cross product, we're going to have stuff with i's minus stuff with j's plus stuff with k's. And now when you cross out maybe the first row and the first column sort of deal, right? Let's go ahead and do this. And now this isn't really multiplication, but it's going to be the partial of r with respect to y. So I'm going to do r sub y, and then minus the partial of q with respect to z. All right, so hopefully you see how this is working. Now let's go ahead and cross out that first row and second column. And so the partial of r with respect to x minus the partial of p, the derivative with respect to z. And let's go ahead and erase those. And then finally we cross off the first row, third column, and we're going to have the partial of q with respect to x, subtract away the partial of p with respect to y, and we'll erase these. Okay, and so one more, let's do final simplification here. We're going to have ry minus qz, comma, maybe pz minus rx, comma, qx minus py. And this right here is the curl. And the claim is, right, this third component right here, this q sub x, p sub y, right, this should look familiar. This is the two-dimensional circulation at a point. And remember, this came up when we were integrated in Green's theorem. So the claim is when we upgrade Green's theorem to something called Stokes' theorem, we're going to upgrade from just this q sub x and p sub y into, well, this entire curl vector, as it turns out. Also notice that we had this whole thing, q sub x minus p sub y. If this is equal to 0, this is only true if this q sub x is equal to p sub y. This was the condition in the component test, right? This was the main thing in the component test. If you wanted to show that you had a conservative vector field, and right, we like conservative vector fields, right, because they have path-independent line integrals, right? In order to have that work out, right, you needed that these mixed partials, right, this q sub x and this p sub y, these should be equal to one another. Okay, so this is very interesting. And it turns out we can upgrade then, and this is the one that we're going to be focusing on here. So if we have a vector field f in R3, and you have component functions are continuous, right, they're relatively nice, then notice if the curl of f is equal to 0, then f is going to be conservative. And so remember, these are path independent. That's why we like these things, and we use the fundamental theorem of line integrals to calculate them out. Remember, conservative at the heart, it really means that it comes from a potential function, right? So we can go out and find a potential function, right, that has the gradient, whatever the vector field is. And so again, we saw back for our regular component test, the q sub x equals p sub y, right? If you subtract this over, that gives you this is equal to 0. So that we just basically had that the third component was equal to 0 when we were doing the two-dimensional component test. Now we're upgrading to a three-dimensional component test. And this is it. The curl of f is equal to 0. All right, let's get some practice actually using this. Here's an example. Consider this vector field. Show that f is a conservative vector field, right? That it has a potential function. Okay, so we're going to compute the curl and show that the curl is equal to 0. So I'm going to compute curl of f. Remember, that's del cross f. And let's go ahead and compute this out. We have i's and j's and k's. And we're going to do a partial with respect to x, a partial with respect to y, a partial with respect to z. And then we're going to input our components. So here we have y squared z cubed. Here we have 2xyz cubed, and here we have 3xy squared z squared. A little scrunched together there, but that's okay. All right, so we're going to have stuff with i's minus stuff with j's plus stuff with k's. And I should note here, right, when I go and I compute my curl, right, I have not memorized. I have no idea, right, if you told me what's the result, right, what does the curl look like, I have no idea what this is without actually computing it out. If you just try to memorize this, I guarantee you will get one of them mixed up unless you have just an amazing memory. And so when I memorize what is curl, I think of it as the cross product, right, and I compute this out. So let's go ahead and do the computations here. In fact, you should pause the video for 30 seconds, try this on your own, and then I'll spoil the surprise for you. All right, so here's my result. And of course, when we calculate this all out, we're hoping for 0, 0, 0, right? That's what it means to be conservative, that the curl is equal to 0. Okay, and so let's go ahead, we compute these partials, right? And we kind of do the whole subtraction stuff. And this is what we get. We indeed do get 0, 0, 0. Now I should mention, right, when you go and maybe you complete quizzes and exams and things like this, right, it's very important that you have this step right, that you show this step, right? That's the whole showing your work bit. Yes, they should be the same, and that's a good way to double check yourself, but right, you want to make sure that you get these components correct. So again, maybe if you cross off the first column and the first row, it's the partial with respect to y of 3xy squared z squared, right? And so when you do that, that 2 comes down and you get 6xy z squared, right? And so you do have to calculate this out. You have to be careful. We want to show that this equals 0, 0, 0. Okay, so since we calculated out the curl and saw that this was 0, this means that it's conservative, which means that there's some potential function, right? There's a function f. So that way, if I take the gradient of f, we get our vector field. So let's go ahead and figure out what that f is, right? So if I do maybe f sub x, right, this should be equal to my first component. That's going to be y squared z cubed, right? We go back up to my vector field here, right? If this is indeed the gradient, right, that first component should be the partial with respect to x. So something like this. And so if I want my potential function, let's integrate this thing with respect to x. So I'm going to integrate y squared z cubed with respect to x. And when I do that, well, this is just constant with respect to x, so I'm going to have x y squared z cubed plus a constant, right? So when you do the indefinite integrals, you always get a constant. But the big thing here is that when you take a derivative with respect to x, if you have, it's not just constants now that you disappear, but any function that has any function that has y's or z's would disappear. So this is kind of like a constant function, but it depends on y's and z's, and when you take an x derivative of this, you wouldn't be able to tell, right? Because they all go to 0. All right, so now let's go ahead and use these other pieces to try to solve for this c function. So if I go ahead and if I take the derivative of my f with respect to y, So if I take this derivative here, with respect to y, I'm going to have 2xy z cubed plus the partial derivative of this function with respect to y. Okay, again, if my original vector field is supposed to be the gradient field, well then this should equal the second component. So let's go up here and take that second component, 2xy cubed. 2xyz cubed. And notice that these two terms right here are the exact same, right? So they would cancel out, and this would give me that the partial with respect to y of our c function is equal to 0, right? Once you kind of canceled both of those out. And so if the partial with respect to y is equal to 0, this means that it doesn't depend on y at all. So actually that our function, c of yz, actually only depends on z. So it's a function with only z's in it. Again, if it had any y's in it, then the derivative wouldn't be 0, right, with respect to y. So this is indicating, right, that our function only has z's in it. So now I need a little bit more room. Let's go over here. And so now my function, it's looking like f is equal to this x, y squared, z cubed, plus, and now it's a function that only depends on z's, right? So I've actually gotten someplace. Now let's go ahead and take the z derivative. So this is going to be 3xy squared z squared plus the derivative of c with respect to z. Right, we're taking a z derivative. And again, if my vector field up here is supposed to be a gradient field, right, this right here should be that f sub z. So let's go ahead and set that equal. So 3xy squared z squared. And notice again that this and this are perfectly equal to each other, so we could subtract away, and we would get that c sub z of z is equal to 0, right? So that means that the derivative, if you take the z derivative of this function, right, you get out 0. Well, that means that it had to be constant with respect to z. So it's constant with respect to y, and it's constant with respect to z, which means that our function right here, this c of z, is actually a true constant, right? That it doesn't have any z's in it. And we already indicated that it doesn't have any y's in it either. So in this case, this is a true constant. This will not always be the case. We'll show some examples in class, right, where this is not just a true constant. We'll be able to get kind of other more complicated things, but this is a good place to start. Okay, so our overall potential function is x, y squared, z cubed, and everywhere that I see c of z, I'm going to just put a true constant, c. So this is my potential function. And if you were to take the x derivative, again, you should get the first component. If you take the y derivative of this, you should get the second component. If you take the z derivative, you should get the third component, right? That's what it means to be a potential function, right? The gradient of f should equal our vector field. All right. So there's an example to show you what we can do with the curl. The last bit, well, I told you that this is called curl and divergence. I should tell you a little about divergence, right? So divergence of f is a scalar function. So, right, unlike the curl is a vector function, right? It has a vector output. Divergence is a scalar function, and it comes from this del operator when you dot product it with f. So that is the partial with respect to x, the partial with respect to y, the partial with respect to z, dot with f. And usually we denote these things with p's and q's and r's, right? These are the components of f. And so this is going to be the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. And it may not be clear at this point, right, what the divergence is actually giving us. We'll talk about this a little bit later in class. But right now, let's actually just compute it out, right? So let's do this mini example right here. Let's compute the divergence of f. And this is pretty nice, right? So if I'm going to take the partial of the first component with respect to x, that's going to be z. The partial of the second component with respect to y, that's going to be xz. And this partial of the third component with respect to z, that's going to be 0. So in this case, the divergence of f is equal to z plus xz plus 0. Of course, we can simplify that down, z plus xz. And if you'd like to, you can factor this. But notice that this is a scalar function, right? It's not outputting a vector, it's outputting numbers, right? So depending on what x and z are, it's going to be outputting a scalar rather than a vector. And that happens anytime you have the dot product. Okay, that's it for this video. I'll see you guys later.